Multiverse review. Okay, colleagues. So this is super hacky, super live, zero preparation. We're gonna watch Felix once again. So like one of these days, you haven't had enough sleep. You walk into a first seminar, and then there's a kid who does a presentation on the multiverse. Right? This is what we're gonna imagine happening. Right? So I'm gonna, as you know, with all the meme presentations, I always take it too seriously, and I'm gonna try to treat Felix as if Felix is a student in our course, Philosophy of Science, and I'm gonna try to treat his presentation as a presentation in Philosophy of Science. Immediately, I should say that he tries to cover too much. We'll see how far we go. Anyway, so this is super hacky. I have no idea if this is gonna work. Let's try to start somehow. Felix, take it away.
Edgar, wake up.
That's right, everybody. Today I'm explaining multiverse theory to my Don. Yeah.
Are you awake?
Yeah. So this is not going to be an educational video. Do not take what I say as facts. It's just a way for me to see if I understand it. Then I should at least be able to explain it. Right, Edgar? And I think it's really freaking cool. So hopefully this will spark some interest for other people rather than me saying, okay, this is how it is. Don't do that. Don't listen to me. I'm just explaining to my dog. But, we're all familiar with multiverse theory. We've all heard about it in some sort of sci-fi movie or regular movie in general. They always come up. Everyone knows about it. But I want to understand, how does it actually work? What's the actual idea behind it being theoretically possible? So I found the experience of trying to understand multiverse theory extremely annoying. Because when...
Yeah, okay, so... first of all, it's amazing that Felix is doing a video on the multiverse. Again, I keep talking about Aristotle, Aristotelian ideal of a flourishing of human potential, developing or rich in varied abilities. All men by nature desire to know, says Aristotle. And this is what Felix is doing here, right? So he desires to know, and he desires to share his knowledge with us. And this is beautiful, this is wonderful, this is, I want to say, Felix, he wakes up in the morning, he can do whatever he wants with his life, but he decides to upload a 30-minute video explaining the multiverse to us, right? This is amazing public service. I'm all for that. If this was a real presentation in a class like ours, half an hour is a bit too much. This is going to go for 30 minutes. I'm speeding this up a little bit. Half an hour is a bit too much, and also, multiverse has different meanings. And he smushes them all together. This is Max Tegmark's fault. I'll talk about this hopefully in a second. I should also say that the previous time I did this was a much simpler topic. Pewdipie was talking about, Felix was talking about Plato's Republic. And there was a much more self-contained topic. This is talking about too many things at the same time. In order to do this topic justice, Sean Carroll, I'm a huge fan of Sean Carroll, has 24 lectures and 24 question and answer sessions. So 48 hour-long videos. So, and Felix is trying to do this in 30 minutes, but it's a good effort. It's a good effort. But if you want to learn more, Sean Carroll is a good place to start. Both his books, but maybe more importantly, Sean Carroll's videos on YouTube. We should go back to Felix. One thing I want to say immediately is that I'm extremely grateful to Felix for everything he does, and I can imagine so many people have tried, to use Felix's help to go through some difficult points in their life. Definitely when I was in dark and depressive places, Felix has helped me out tremendously in the past. I don't really watch his videos regularly these days because I have too much work. But, I was really excited when I saw this in my feed, so much so I could barely get any sleep. And I dropped basically everything else I was doing, and I thought I should record this right now. Partly because we're covering similar topics in our Philosophy of Science course, and I thought I'd use this opportunity to fill in some of the blanks. Also, another thing I want to mention is, Felix talking about Plato. I have actually used my live stream on Felix explaining Plato's Republic as preparation for my Coursera lecture series course, which is out today. Today is a super crazy day for me. So I need to be recording the next lecture for Philosophy of Science. My introduction to political philosophy is out today, And I'm trying to do Felix at the same time. But, what can you do? What can you do? Also, I have to say, so this is obviously a shameless plug, me talking about Coursera, but the way this links together is that Felix is going to talk about materialistic worldview from protons to presidents, right? The multiverse and those kinds of ideas. And I try to teach my course in moral and political philosophy from a completely materialist standpoint. So this is my plug for my philosophy of science course. Anyway, I'm sorry, Felix. Back to you. Let's listen to what you have to say. So we're going to talk about the multiverse. Explained in 4 levels. Again, this way of slicing multiverse into 4 levels is due to Max Tegmark. We had an occasion to mention him already in our first class. Anyway, let's listen.
What happened was new terms that I have no base knowledge of these things, but new terms would always come up while trying to understand something. So I have to look up what that means. And while looking up what that means, another term comes up and I have to look up what that means. And then when I look up what that means, another term comes up and then I have to look up what that means. And I'm just getting further and further and further away from actually understanding anything. But that ends now. The goal of this video, it might not be the most perfect explanation, but I want anyone to watch this and try and understand as well. That's my goal. We're going to keep this simple, baby. And we're going to keep this crystal clear so even my dumb dog Edgar understands. You are watching this video now, but in the video, if you make it through, you're going to be like, huh, I get it. I get multiverse theory. That's what we're doing. Now, I said that I got really frustrated, but in reality, a lot of these things that annoyed me at first turned out to be really, really cool concepts and ideas that I actually found really, really interesting. So trying to understand multiverse theory and all that has actually been really, really fun. I love doing this. And this video is more of me being excited and wanting to talk about it. So take it as that. Again, not an instructional video. So, multiverse.
Yes. So once again, see, the biggest, the most important ideas in the universe. And somebody like Felix, who can afford to do anything he wants with his time, spends time understanding this. This is exactly the kind of attitude I want us to have in our course of philosophy of science, which we've only begun last week.
Multiverse theory is generally, as far as I understand, divided into 4 levels. So there's level 1, level 2, level 3, level 4. And I don't think there's a specific reason to why they're called levels. It's not like you have to go from one level to another. It's just a way to separate all these different ideas. So we're going to start off with level 1, and I'm going to stop at level 3. But they're amazing, and it's super fascinating. So let's start off with level 1.
Yeah. So basically, this is I think this is Tegmark's presentation. So again, by Max Tegmark, this idea of talking about this so Sean Carroll is my go-to source if you want to learn more about this. So Max Tegmark is a Danish-born physicist who works in, who knows, England somewhere. And he tries to present the ideas of the multiverse in 4 levels. But these are not really 4 levels. These are like 4 aspects. They will not necessarily be related. Some of them are going to be completely unrelated. Felix says he's going to go through level 1 to 3, not talking about level 4. I think the level 4 is most interesting. The level 4 is trying to derive physics from mathematics. Some students have already actually asked me about that in the first seminar. I had an occasion to mention this. So before we proceed, maybe it's a good idea to lay this out a little bit. So usually, obviously, if this was a presentation in class, I'd let the student talk. But because I've only seen the video once and I've seen it very briefly, I skimmed through the video, so I only have a barest understanding of what Felix is going to talk about. So you have my live reaction. So level 4 is going to be the idea that is like mathematical realism. So you imagine the landscape of all the possible mathematics that can give rise to any kind of physics. You imagine this landscape, which is probably going to be infinite, right? And then you imagine that all mathematically realizable structures are realized somewhere. So this is like, you see, ideas, we talk about mechanicism versus teleology, the mechanistic worldview, from protons to presidents, from protons to presidents. How do you get from protons to presidents? And the most important idea is evolution. And the most important mechanism of evolution is selection. So here, this is cosmic selection. I'm starting from the level 4, which Felix is not going to cover. Cosmic selection, right? So Tegmark imagines, there's no serious way to test this, but Tegmark imagines this, and it's like, this is basically how evolution works, right? So you, like monkeys typing on a typewriter, you produce random mutations, and then you select for the favorable ones, right? So same fashion. Imagine that all the possible laws of the universe, so this is one attempt at summarizing the laws of the universe. This is the Lagrangian of the standard model of particle physics. But you can have different equations. So imagine the landscape of all possible equations. So landscape of all mathematically consistent, right? So mathematically consistent formulations of laws of physics, right? And then the idea is that this is selection bias, and like this is called anthropic principle. Obviously, we find ourselves in the patches of this vast landscape in which it is possible for complex life to exist, because the vast majority of these mathematical laws are going to lead to emergence of universes in which nothing complex can emerge. Chemistry probably is impossible, molecules are impossible, complex life is impossible, consciousness is impossible. So we find ourselves in this vast infinite landscape. We find ourselves in smallest, tiniest patches in which complexity is actually possible. This is a way of solving the fine-tuning problem. Again, all of this ideally, if we were to explain this again, Sean Carroll has 48-hour-long lectures explaining all this, right? So I'm obviously doing like a super brief pass through all of this. Every topic here deserves a whole separate video, deserves a whole separate presentation. Colleagues, if you're interested in this, by all means. So fine-tuning and this is called the weak anthropic principle. The strong anthropic principle, for my money, is wrong. As far as I'm concerned. But the weak anthropic principle, this selection effect, that we find ourselves, obviously, in places which can support life. Why doesn't he like my word? Fine-tuning. Fine. I absolutely cannot spell this time of day. Anyway, so this is going to be the fourth one, something Felix is not going to talk about, but I wanted to mention this. And again, this is a way to realize the project of Pythagoras or Plato, derive physics from math. This is one way of doing this. It's not the most elegant or the most parsimonious way, but it's a possible way. Okay. Back to Felix, and we're gonna go back to level 1, which is gonna be the simplest level, but also very interesting. Felix, take it away.
One you're probably already familiar with in some sense. It's the first one I've ever heard about, and it's the idea that our universe, or if there's infinite universe or infinite space, since you exist by mere chance, if a space out there is infinite, then by mere probability, sheer probability, there will have to be another one of you eventually out there.
Notice how Felix says, you exist by mere chance. Immanuel Kant, der Schlund des zwecklosen Chaos der Materie, right? This universe is the abyss, according to this formula, the abyss of the purposeless chaos of matter. We are products of random chance. And if the universe extends far enough, then anything that can happen at some point will happen, right? So obviously, certain things are impossible. So it's important to keep this in mind. So some things are just impossible. So let me give you an example. So according to this formula, an electron spontaneously turning into a positron, that's impossible because there are conservation laws. But anything that is in principle possible will be instantiated somewhere. Numberphile, another great YouTube channel, Numberphile. Let me give a plug, right? So I talk about Sean Carroll. Another wonderful channel is Numberphile to explore this. Another great channel, probably the best channel if you want to understand the physics of this, is PBS Spacetime. Matt, first name's Matt, last name I forget. Matt O'Dowd, I think is his name. So Numberphile talks about huge numbers. If you look up Graham's number, right? So it's a way to visualize really, really, really vast spaces. Obviously, human brain cannot process this, but it's like if you imagine space extending, through such a long, stretch, anything that can happen physically will happen at some point, just given enough time. It's like when you throw dice. At some point, every weird combination will come up. If you throw dice 1,000,000 times, 1,000,000,000 times, 1,000,000,000 times, 1,000,000,000 to the power of 1,000,000,000 times, you understand the Graham's number is much bigger than all these. So this is one example. Obviously, also, when we're talking about the universe, notice, and Carroll, Felix is going to talk about this in a second, we're talking about observable universe. Observable universe. So our patch of observable universe is, I think, 93 billion light years. this is the space that we can observe, right? But beyond this space that we can observe, we imagine probably it's impossible to test right now, but the smart money will tell us that the universe just continues in the same fashion. And this is what Felix is talking about. Nietzsche, when he talks about eternal recurrence, and kind of Poincaré has similar ideas, Nietzsche's eternal recurrence kind of has a similar vibe, right? So in this abyss of the purposeless chaos of matter, the universe is not moving towards some grandiose conclusion, but throughout space and throughout time, there's more of the same. And all these horrible things, the breakups, the genocides, the murders, the tortures, they will, they exist in this patch of space, and they will continue indefinitely into, all the regions of space. And just by pure chance, you'll get patches which are better than ours, but also patches which are worse than ours. Anyway, back to Felix. I'm sorry, I interrupt Felix too much. I should let Felix speak more.
It's sort of picturing that our universe is a random structure of particles that just happen to be. And it's just a matter of, okay, well, how far would you have to then travel for the probability of another same set of particles being structured in the same sense? I remember hearing about this multiverse theory in, I don't know if you've seen this movie, The Beach, where Leo is like making kind of, let's see what he says.
I mean, there are infinite worlds out there, where anything you want to happen does happen.
So be careful. Not everything you want to happen does happen, but anything that is physically possible, given enough time, will happen. So some things, like square circles, just never happen because they're, as far as we can tell, probably physically impossible.
Richard, you know something? This is just the kind of pretentious bullshit the Americans always say to French girls, so they can sleep with them.
Shut up, mate. It's cool. It's cool, right? It's cool. It's cool to imagine the idea that another version of you is out there. Right, Edgar? It's also kind of hopeful in a way, If things are here, at least in another universe, someone else is doing way better. We can only hope I'm in the good universe, right? You're having a great time, aren't you? Yeah, do you understand? So this is generally seen as the least controversial idea of a multiverse. So picturing space and how big it is something I wasn't really familiar with. Apparently the way we distinguish it seems like I just didn't pay attention in school at all, but apparently the way we distinguish our universe is what we call our observable universe, and it's basically how far light has traveled since Big Bang. Anything beyond that we can't see because light hasn't reached those areas yet, and it spans 42 billion light years. So even
So observable universe. I realize I'm not sure because I have this hacky solution to jump between Felix and okay. So this is how I make it. Yeah. So I was talking about Sean Carroll, number file PBS spacetime. Some things are just impossible. Observable universe, 93 billion. So observable universe. This is an important concept. Okay. So when we talk about the universe in our course, we always talk about observable universe because who knows what is beyond our observable universe. Sorry, Felix, for interrupting. Back to you.
Even though you try and imagine infinite space, to me that makes more sense that the universe is infinite, because if it's finite, then what the f is beyond the edge of the finite? Is there just a sign that says, hey, space ends here, stop here, can't go further? But I guess in a sense we do have that with our observable universe, but we do imagine that whatever's outside our observable universe is just like space inside our universe. Cool. Great. Max actually did a really cool experiment. Max Tegmark, I think he's the one that categorized multiverse theory into these levels. And he actually did a calculation to see, okay, if we are just random particle structured, how far would we then have to travel to reach another multiverse, an identical parallel universe, rather, sorry. And he came up with the number 10 to the 10 to the then raised.
Yeah, okay. So 10 to the 10 to 100... sorry. 11.8. How do you say this? Does this work? Does this work? Does this work? Okay, I apologize. My streaming skills are subpar so far. Yeah. So so this first level of the multiverse is if you go 10 to the 10 to 118 meters. By sheer probability, you will bump into your identical twin. Molecule for molecule identical twin. Let me write molecularly identical twin. Think about that. Think about that. Somebody who is exactly like you, who has exactly the same physical structure as you, and who has exactly the same feelings, hopes, aspirations as you, just by mere probability. So this is the simplest level of the multiverse. If, again, beyond the edge of our observable universe, these kinds of laws of physics continue, then by sheer chance, you are likely to bump into your identical twin if you travel 10 to the 10 to 111 meters. And of course, if the universe extends infinitely, then you will bump into infinite number of variations, and you will bump into infinite number of variations, like tiny variations of you, like the same you but with a slightly different molecule, right? And like everything that can physically happen will happen. Again, some things just might never happen, but within the realm of possibility, more or less everything will be realized. Think about that. So it's a mind-blowing thought. It deserves a whole separate hour-long video. Let's just take a moment to appreciate that. The vastness of the universe. Okay. Vastness of the universe appreciation moment finished. Let's continue with the stream.
118. Is that meters? Doesn't sound that far, right? You imagine that 4 times 10 to raise our universe is 4 times 10 to raise 26. That doesn't sound far at all. That's 14 billion light years. You try to imagine that number? You can't. You just can't possibly even picture how far that is. But it's kind of cool that you can imagine how far to travel for another universe. That's a good picture to draw for our observable universe. Moving on. Everyone satisfied with the multi-layer 1 multiverse theory? Yeah? Random? It's kind of weird to imagine that you exist by sheer probability, right? I don't like the thought that much, to be honest. So, universe big? Anything can happen. That's basically your level 1 multiverse. Oh, your tongue is out.
Universe big, anything can happen. Well, not anything, but anything within the realm of possibility. Again, presumably, electrons don't turn into positrons. 1 plus 1 is still equal to 2, and within Max Tegmark's picture. And circles are not squares, squares are not circles. Even if you go far enough. That's an important pedantic note from me as a philosopher of science.
Now, you ready for Multiverse Level 2? I think this is where it gets really interesting. So Level 2 uses this fantastic discovery that I had never heard about. I wonder if now that probably a lot of you who are younger than me are learning about this in school, but it's a cosmic microwave background, which is basically sort of map of our universe. It's the oldest radiation that exists in our universe, and they dated it back to 380,000 years after the Big Bang. So discovering this cosmic microwave background also is a great proof for that the Big Bang did happen, even though there are already many things, evidence for it. Okay? We're not here to debate that. But the
should I mention this? So yeah, CMB, cosmic microwave background, is fabulous for all sorts of reasons, right? But it's like, to a large extent, when we talk about the Big Bang, it's not just, blind religious faith. You can point to observations that you can do right now to see evidence of Big Bang, right? And CMB is not exactly the Big Bang, but it's the afterglow of the Big Bang. So you can look, using the appropriate device, and you can see that all around us, there's light which is traveling from the earliest time in the universe, when the universe was much hotter and much denser, which is basically what we mean when we say the Big Bang. Because the exact moment at time equals 0, we don't understand very well, and Felix is actually going to talk about this in a moment. Felix, continue.
Cosmic microwave background is the sort of thing that just gives a lot of information about our universe. But it also gave us information that sort of makes things difficult to understand Big Bang. You're so cute. Look at you. So while examining the cosmic microwave background, scientists discovered 2 fatal flaws, or big problems that are very perplexing. And the first one is the horizon problem. I don't know, I just think this is so interesting. So if you look at the cosmic microwave background and you look at 2 opposite ends of it, you're looking at 2 opposite ends of the universe. And what they realized was that these 2 different ends of the universe are way too uniform. By the decimal to the decimal to decimal, I don't know how to express it, but they are so uniform that they would have had to been in contact at some point. It's kind of like how you mix 2 fluids together, right? You mix G fuel with powder, eventually it finds a uniform taste. This is the greatest example I've ever done. Can you sit still? I'm trying to explain to you. So this is the horizon problem, but the real problem about this is that to travel in between them, they are so far away that it would take longer to travel between them than the universe have ever existed. So theoretically, it's impossible for these to be that far apart. So how can 2 pieces of the universe be so uniform alike that they would have to be close at some point and be so far away? Focus. So that's...
Yeah, so this is, he's going to talk about the horizon problem and the flatness problem. It's a bit technical, a bit into the weeds. I'm not even sure I want to comment on this, but these are examples of the fine-tuning arguments. The initial conditions around the time of the Big Bang seem to be very special. They seem to be finely tuned, placed in by hands. So you have appearance of design, appearance of order, if you want, appearance of teleology. And the way we explain away appearance of teleology has always been the same since the time of the ancient Greeks, since the time of Empedocles, and since the time of Democritus and Epicurus. We explain it away through, random process generates an array, and then you select from that array. And just by pure chance, if your array is large enough, you generate elements which appear finely tuned even though they're not. Inflation is not exactly about that, but it's in that spirit. Again, if you're interested in this, do a presentation.
It's one issue. The other issue is the flatness problem, which I really struggle with, and I think I've learned everything about it, and at the end of the day, all you really have to understand is the universe is really flat. In fact, it's so flat that it's puzzling just how flat it is. That's the flatness problem. And I don't know how much detail I should get into this. It's one of those things where I just went around in circles and like, what does flat mean? How can the universe be flat? I don't really understand any of this. I don't know what the best way to explain it either. There's a bunch... Hello? So, I guess all you need to know, in scientific terms, without complicating things too much, there's something called the density perimeter. It's this omega sign that you see. And it sort of helps us determine what the shape of the universe is. The density perimeter is based on, I think, gravity and mass. The density perimeter is the ratio of the average density of matter and energy in the universe to the critical density. Oh, thank you. I totally understand what that means. To be honest, the math behind it, we're not going to understand, so it doesn't really matter. What you do have to understand is that if this density perimeter is bigger than 1, the universe shape will be a sphere-like. If it's smaller than 1, the shape of the universe will be bent like a struch. I don't know what it's called. And if this is 1, it's flat. It means the universe is flat. So, I gotta be honest, I'm not 100% sure.
Yeah, so the shape is called a saddle, Riemannian, negatively curved space. Should I talk about this? We could go into the weeds and explain. So again, the Felix is talking about two problems. The first is the horizon problem, and the idea is that the universe has been expanding. Well, as far as we can tell, at the current expansion rate of the universe, there would not have been enough time for different parts of the cosmic microwave background to reach thermal equilibrium. But they are in thermal equilibrium. So the inflationary hypothesis, Alan Guth, basically hypothesizes that they were in contact at some point in the past, and you had this inflaton field, which may or may not be the Higgs field, or like the Higgs field, if you know what Higgs field is. And the idea is that all of observable universe was in contact at some point, so within space-time light cone, right? So within the reach of the speed of light. But then you have this inflaton field which has expanded space dramatically. So this is the horizon problem. And the flatness problem is that in Einstein's equations, matter and energy curve, bend space-time. And basically, it's very difficult in Einstein's equations to get the universe, if Einstein is right, it's very difficult to get a universe which is perfectly flat. It's either going to be negatively curved or positively curved in 3 dimensions. Obviously, we're using 2-dimensional analogies, which is kind of difficult to do. Both of these results seem, again, they appear too improbable to have arisen simply by pure chance. Like if you generated universes at random, according to Einstein's equations, it would be rare to find a completely flat universe. It would be very, 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 very rare. So inflation tries to propose a mechanism as to what happens. Well, anyway, let's go back to Felix.
I understand this, okay? But they draw this example with triangles, right? If you add up all the angles of the triangle and it's 180 degrees, then that means it's flat, right? If it's bigger or smaller, then that means the universe have these two shapes. And I suppose you can do that with the CMB data.
Yeah, so you have to be careful. So Felix was showing, again, 3-dimensional objects, curvature, 2-dimensional curvature on 3-dimensional objects, right? So this is an imperfect analogy because we're also imagining that the 3-dimensional space-time is curved in the 4th dimension. So the analogy is imperfect, but let's continue.
Picking points that are very far away in the universe and sort of tell if the angles add up.
You can see this is a much more difficult video than talking about Plato's Republic.
Does that make sense? I gotta be honest, I'm not entirely sure if that's exactly how they do it, but that makes sense in my head at least. Because things can appear to us as flat, like this picture D here, even though they are a sphere. So we need data that are really far away, and I suppose you can do that with the cosmic microwave background because it maps our universe. But the problem is, I suppose, what they found is that the universe is super flat. What would have been cool if the universe wasn't flat is that we could actually calculate the size, because we would know the curvature. And by that logic, you can then calculate the size of the universe. So the thing about this density perimeter.
Yeah, so we have, because always when you do observations, there are error bars, and so our current understanding, we have a lower limit on the size of the universe. If the universe is a 4-dimensional sphere, if the universe is curved and is therefore a 4-dimensional sphere, such that you can go in one direction, and if you go far enough, you will go back to where you started, in the 4th dimension, right? So because the universe in our local patch, 100 billion light years, appears approximately flat, there's a lower bound on what is the minimum size of the universe. And it's some ginormous number that you can look up.
Is by when time passes, it naturally curves. Okay, that's all we need to know really from what I've all said. We have this way of measuring the curve of the universe, and naturally, the more time passes, the more it curves. And if you imagine from the point of Big Bang to the size that the universe is now, the preciseness of, if this was completely flat, the preciseness of that in the beginning, from what I understand, just is too precise. It just seems so unlikely that we would find ourselves in this flat universe with Big Bang in mind, right? I hope I make sense here. I wish I could be like, any questions, because I don't really get it either, so help me. But I think in reality, all we need to know here is that there's the horizon problem, two different parts of the universe are way too like, and the flatness problem, which is that the universe is too freaking flat, dude. It's too flat, my dude. So flat, dude. In comes to explain this inflation theory, and it proposes that the universe rapidly, I don't know if rapidly even remotely begins to explain just how fast inflation happened. It means that the universe expanded faster than the speed of light, from being the most smallest thing we could ever observe to the size of our observable universe.
Yeah, so inflation happens faster than the speed of light. And it's not breaking Einstein because it's not anything in space moving faster than the speed of light, but the space itself expanding faster than the speed of light.
In a matter of a fraction of a second, even fraction of a second. Our universe had this incredible, unbelievable exponential growth in such a small period of time. I had never heard of inflation theory before, and in the beginning it was just really confusing because you never heard about it, right? What the fuck? What is this cosmic inflation shit? Maybe they teach kids this in school now, but here's a cosmic microwave background. Here's where inflation happened. So just a tiny portion of our time span in the universe. Inflation. Imagine instead of the Big Bang, imagine the big, I don't know how to explain it. But I think the cool thing about inflation is that...
Yeah, so actually, I want to get to the many worlds interpretation of quantum mechanics, so I don't even want to comment too much now on what Felix is saying, but let's continue.
You know, you're taught that nothing can travel faster than the speed of light in school, right? But it kind of makes sense that space itself can expand as fast as it wants. There's no rules on space being bigger. It's just what objects in space can travel. That is the limitation. So this inflation theory doesn't break any laws of physics and conservation with energy or anything like that. And Alan Guth, who came up with this theory...
Yeah, so Alan Guth is the person who's, most credited with inflationary theory. Inflationary theory has its own problems. Maybe we'll do a video at some point on this, but it is a kind of very strongly considered possibility for now. I talked yesterday about, betting a house, betting a car. I think most physicists would be at least willing to bet a car that something like the inflation has happened.
Explains it that we normally look at gravity as some sort of attraction with objects, interstellar objects, attracting and swinging each other around. But gravitation can also be repulsion. So what he says is that the universe was uniform. They had the uniformity before inflation took place, and it was flat before inflation took place, which makes sense. It would make way more sense that in the beginning it was flat anyway. And then from this tiny universe, this is so weird to think about, it then inflated to the observable universe that we have today. And it sounds sort of fanatical and crazy, and I kind of don't even know if I believe it, to be 100% honest. But there has been evidence of inflation theory with quantum fluctuation ripples or some shit like that. I don't really get it. I'm not getting into that. There's evidence of inflation while monitoring the CMB. Is basically all I'm going to say about it. And it sort of beautifully explains these two problems. Inflation theory also creates, the reason why I'm making this video to talk about multiverse theory, it creates a problem, which is the fact that once inflation starts, or almost all version that explains inflation, eventually leads to that there's no reason that inflation should stop. And here's where I get kind of confused, and I'm going to try my best to explain the way I understand. If anyone would help me in the comments, I would love it. So from what I gather, is that this gravitational repulsion comes from a certain state of mass. And this mass is unstable, and it can decay randomly, like a radioactive substance or something like that. So it starts decaying, but by the time it has decayed in certain patches, it has already increased in size larger than itself. So this decaying mass is like a local Big Bang, which means that our Big Bang is one out of infinite Big Bangs. Inflation is just... Oh, decay, Big Bang. Hello, I'm explaining this. Inflation, okay. Imagine this shit. Keeps going. Inflation. Local Big Bang. Are you asleep? What is this video? Why did I... Oh, God.
Okay. So, let's try to maybe get a handle on that. So we're talking about Max Tegmark and his 4 levels of the multiverse. So the first one is, just the universe is so big. The second one is this idea of infinite inflation, right? So the notion is that you have some kind of a process, a mechanism that generates Big Bangs. That our Big Bang is not the beginning of the entire universe, but it is only a very special moment in the history of our particular observable branch, right? But it's like if you imagine maybe like a lava lamp, and you have these bubbles of wax, bubbling to the surface, right? So this is kind of what infinite inflation looks like. So you have this inflation going on, and then it stops in particular patches, but it continues in other patches. And what infinite inflation gives you is it gives you infinite Big Bangs. Infinite inflation gives you infinite number of Big Bangs, potentially with different conditions, potentially with the different values of the variables or free parameters in this, in these kinds of formulas, like the fine structure constant or the anomalous magnetic dipole moment of the electron, that kind of thing. So it is a way to monkey typing on a typewriter. And monkey types on a typewriter for 1 billion years, and they type Shakespeare. This is what infinite inflation does. So you have this nucleation of baby universes, which goes on for forever, infinitely, basically. And it generates all the possible universes with all the possible parameters, with all the possible variations in laws. And so you get this huge landscape. And again, if you generate laws of the universe randomly in such a fashion, then most of the time these universes would not be able to support anything complex, anything interesting. You would not get chemistry. Again, you would not get biology. You would not get consciousness. So again, so we find ourselves, again, this weak anthropic principle, we find ourselves in patches of the universe where, life can exist. So you see, number 4, cosmic selection. You have this landscape of all mathematically consistent laws, and level 2 infinite inflation is kind of a way to realize that through this inflaton field. Now, inflation is not a complete theory, and there are ways in which inflation can work with string theory, for example. And, it's like string theory is one way to generate an array, a huge array of possible laws of the universe. Let's say numbers of dimensions, like we find ourselves in 3 spatial dimensions, but it's thinkable that in other patches of space you can have 4 spatial dimensions or 5 spatial dimensions, or you can have patches of the universe where time flows in a different direction. So all of this kind of, it's like you have this underlying simplicity, underlying simple mathematical laws that give rise to this complexity. So this is the second level of the multiverse, right? So in this 1, 2, and 4, you can see how they are very similar, I hope. And multiverse number 3 is going to be completely different. It's going to be very different. It's going to be actually the most interesting. The reason I'm making this video in the first place, and we're going to get to it in a second. By the way, if you have any questions about any of this, feel free to ask me during the seminar. I'd love to talk about this. Again, you see, Felix, if this was a presentation in class, he tries to talk about these 4 levels, these 4 problems. Ideally, you need to take them one at a time. Okay, it's like if you're doing your presentations, pick one. Don't talk about everything. This is one problem that students sometimes get. Anyway, Felix, let's continue.
Okay. Anyway, I think what's cool about inflation or eternal inflation is that it's scientists looking at how universes are created, what happens before. Apparently, this is...
Yeah, so again, these are ways to look at time before the Big Bang. Again, right now, our best theories of the universe do not account for t equals 0. We do not know what happens at t equals 0. Infinite inflation is one possible candidate as to what happens exactly at t equals 0. Just for reference, there are other possibilities, like, for example, Roger Penrose, CCC. So Penrose, it's called conformal cyclic cosmology. This is another way to generate basically an infinite array of universes to talk about what happens before the Big Bang or what will happen after the heat death of the universe. Notice also, if infinite inflation is true, our patch of the universe might reach heat death, but other patches will continue to expand. So that, our own neighborhood will become bleak and uninteresting, will, reach thermal equilibrium, heat death, but other patches will continue. And again, there's also a possibility, think about Jean-Paul Sartre, a tongue turning into a caterpillar. If infinite inflation is true, there's a calculable probability that we will collide with another universe. And, these 2 bubbles collide into one another, and all of matter potentially could disintegrate in the next moment. And again, this is a serious, to some extent even testable scientific theory. Okay, this isn't just let me imagine that my tongue can turn into a centipede. No. This is a robust way to generate this with mathematical rigor. Okay, back to Felix.
This is the level 2 multiverse and how it's made. And the other ones could even not defy our laws of physics, but they could have different laws of physics based on how the universe is created. There's a bunch of
So have different laws of physics.
Tells on this that it's way too complicated for me to understand. But the general principle is that the problem with inflation theory is well accepted and well understood. But if you accept inflation, you also kind of have to accept eternal inflation. And if you accept eternal inflation, since something is eternal and can eventually lead to a Big Bang, that means it's infinite Big Bangs. I read somewhere that Stephen Hawking's like a couple...
Yeah, so infinite inflation, infinite array of possible laws of physics, infinite Big Bangs. It's very nice, very beautiful.
Couple years ago in one of his last, I didn't really read into it, but I think he was disputing this idea of eternal inflation, and it's still a more controversial piece of multiverse theory than the first one, for example. But to summarize, multiverse level 2, inflation, the big never stop, keep making another Big Bang. That's all you gotta know, baby. You understand?
Yeah, so again, there are different possibilities. I think, Hawking changed his mind a lot. At some point, he thought that maybe our local Big Bang is the beginning of the entire universe. That's one possibility. And again, his scientific advisor, Nobel Prize winner in physics from last year, Roger Penrose, right, has this CCC, conformal cyclic cosmology. So there are alternatives to inflation, is what I'm saying. But that's, inflation is a very robust theoretical possibility. Back to Felix.
Great. Now we're going to level 3, Edgar, and holy shit, okay? Level 3 blew my fucking mind, okay? It's so weird.
Yeah, so notice, level 3 is not going to be level 3 in any meaningful sense. It's just going to be a completely different story, which has nothing to do with things that we have been talking about before, okay?
And so awesome, and I don't believe it, Edgar. So to understand level 3 multiverse, you have to understand a little bit of quantum physics, which I don't understand. A famous Nobel Prize physicist said that if you think you understand quantum physics, you don't understand quantum physics, which is just a play of making you understand just how weird.
This is a famous quote from Richard Feynman. If you think you understand quantum physics, you don't. But, I think, I agree with Sean Carroll. I think that's a defeatist attitude. There are ways to make sense of quantum physics. Sean Carroll's favorite, Many Worlds, is one. My favorite, the Broglie-Bohm pilot wave theory, is another. Maybe we'll get into that in a second.
Quantum physics is, but all you need to know, really, is that quantum physics is describing the smallest parts of our universe: atoms, electrons, protons, molecules, and whatnot. Basically, what creates everything around us, right? Our building blocks of our universe. And as far as I understand, in quantum physics, you describe things as waves, and in comes this wave function. Okay? To me, this is really weird, and I feel like someone just skipped like 50 parts of something. So now you're telling me we can't depict an electron as a particle, but we depict it as a wave. What does that mean? So this wave function is a mathematical function to describe the probability of where we can find an electron, for example, or a quantum particle. Nothing is precise when you're talking these tiny, baby, tiny, small things. So we have to use this probability wave function, right? That makes sense to me. But what we can do is use this wave function to get fairly accurate results, even though it is probability. But from what I understand is that we don't know if the wave function is real because no one's ever seen it. It's just a mathematical way to describe it.
Yeah, so again, this would take about 48 lectures to describe properly. But again, so what Felix is talking about right now, again, this is a different meaning of the word multiverse, right? So you can have like cosmological multiverse, and again, you have this landscape of different laws of physics, or you can have infinite inflation. One example of that, and these are basically levels. So this is 1, 2, and 4 levels, aspects, and then number 3 is the many worlds of Everett's interpretation of quantum mechanics, and this is just a completely different story. This is completely unrelated to what he has been talking about before. So this is due to Hugh Everett. And the most famous proponent of this theory today is Sean Carroll. And he has recently written a wonderful book called Something Deeply Hidden. That would be an excellent entry-level reading on the subject.
Electron. And they did an experiment on it that is mentioned apparently all the time, to the point where people are sick of hearing about this experiment. But I totally understand, because this experiment, the double slit experiment, probably the strangest thing I've ever heard about. And I can't believe I've never heard about it. And if you've never heard about it, what a pleasure it is for me to explain it to you, because it's the weirdest fucking thing I've ever heard. It's so weird. So I actually do remember in school learning about waves and light particles a little bit. So I looked it up. So Thomas Young in the 1800s was trying to determine light. Okay, what is light? Is it a particle? Is it a wave? Apparently there was a whole dispute between Newton and this guy. They butted heads. No, light is a particle. No, light acts like a wave, right? So Thomas Young did an experiment where he shone a light through a slit, and on the back wall of where he's shown the light, an interference pattern showed up. And an interference pattern can only really occur if waves are interfering with each other. I don't know how to explain this better than just showing a picture. So you have light waves, they pass through this barrier, and then it's kind of like water waves, I guess. 2 drops in water, they both interfere with each other, and it creates this sort of striped pattern at the wall. You probably know about this in school, because for some reason I remember this in school. But all you really need to know is that the light wave passes through both of these slits. It interferes with each other, and it creates this pattern. And this can only really occur since it's a wave and it passes through both of the slits at the same time. Okay? That's all you need to understand here. So Thomas Young observed this and was like, light, it's waves. Got him, I proved it. Later on, what Einstein realized was that, no, actually, what the fuck? Light can be both particles and waves. I remember learning this. I was like, okay, sure. Think about it. How can something be 2 things at the same time? It makes no fucking sense. So what these motherfuckers did is they did an experiment on it. And they should never have done this experiment. I'm joking. But it's sort of like testing a paradox. How can things be two things at the same time? And I think that's the thing with quantum physics, is that it just doesn't make sense like that. An electron can be in an excited state and in a low energy state, or whatever it's called, at the same time. Quantum particles can be 2 things at the same time. And that's just a weird thing to try and wrap your head around. So they actually tested this, which I think, I don't know, it just blows my mind with the double slit experiment. And if you already heard about it, yeah, roll your eyes, whatever you heard about it 1,000 times, good for you. But basically what they did is I don't know how, because it must have been extremely tiny, right? They did this double slit experiment, but they did it with electrons. An electron's particle, right? But we describe it as a wave function. So now we're going to find out, what is an electron? Is it a wave? Is it a particle? Because this wave function function has been so far an excellent way to describe an electron, but now we will see in reality. So if you picture this double slit experiment, what you imagine will happen when you shoot, let's say these dots aren't electrons, let's say they are a bunch of eggs. You're throwing eggs through 2 slits in a wall, and you expect to find the eggs smashed on the wall in this type of pattern. Not in the middle, because it's covered up in the middle. This pattern makes sense. Throw egg, they hit the wall. Okay, what happened, however, with the electrons is that it created this interference pattern, where we actually have eggs in the middle, or electrons, rather, which is weird. That shouldn't happen, unless electrons act like a wave. So, as far as I understand, when the electron hits the wall, and when you see it on the wall, that means that the wave function, it has collapsed. So the electron no longer acts like a wave, but has now become a particle, and that's why you see it at the back of the wall. Does that make sense? It's sort of imagining that, ignore these dots here, and imagine a wave. It's a wave, electron is a wave, and then it hits the wall, it's a particle. That's the wave function collapsing. Because when they did the test, the electron acts like a wave, passing through the thing, otherwise it wouldn't be able to make this pattern. It's a wave, hits the wall, wave function collapses, it's a particle. Does that make sense? I think I explained that pretty well. Yeah. So here's what that looked like, right? But what then you could say is, okay, well, maybe they're just shooting, you know, they're, okay, I'm throwing eggs like fucking crazy, or particles. So what you could argue is that, well, the only way for this to happen is if an electron passes through both the slits at the same time. How can one object be in 2 places at the same time? It don't make sense. It don't make sense. It's dumb. I don't even want to think about it. So the theory was that, okay, well, you're shooting a bunch of electrons through, they're probably interfering with each other, okay? They're not passing through at the same time, you dummy. They're just interfering with each other, creating this pattern. So how did that happen? Guess what? It gets so weird. I don't know what to say it. So what they did was, okay, well, all right, cool. How does that happen? I'm sure the scientist said it. Let's add an observer. Let's add a light that detects which one of these slits the electron is passing through, so we can understand what the fuck is happening here. How is this electron acting like a wave? We're gonna add an observer, and we're finally gonna understand how can this electron act like a wave and be a particle at the same time. We're gonna have the proof. We're gonna get it now. We're gonna get that stupid electron. What happened? It's a particle now. You add an observer, the electron acted like a particle. That's just fucking dumb. That's just so dumb. Quantum physics is so fucking dumb. How? So just by adding an observer to an electron, the wave function collapsed as soon as it was observed, as opposed to when it hits the wall. So adding an observer to an electron collapses the wave function. Basically, an electron acts differently depending if it's being observed or not. What? I guess it is a bit of a fallacy to assume that an observer is something passive, because when you're looking at things at such a small level, just by saying, okay, I'm just looking at you, I'm not doing anything, you're still in a way interacting with it by observing with the electron. I think, at least. I'm not sure if that's true or not, but that makes sense in my head. When you say an observer to an electron, it kind of makes it go, wait, well, they shouldn't change, I'm just looking at it. What is it, an anime schoolgirl being shy? Come on, what are you, a wave or a particle? I don't get this shit. So, why does the wave function collapse when it's being observed? And there's a lot of theories behind this. And there's probably better ones, and I didn't look into all of them, but the reason I'm making this video is to talk about multiverse theory. And
yeah, okay. So I've YouTube was telling me that there was some problem with OBS. I hope that the stream is back and is live. So as you can see, this is a very different reaction video to Felix talking about Plato, because this is complicated, this is controversial, there's potentially a lot to say, and I'm not exactly sure what is the best place to start. So let me try to give you some rundown. So again, Max Tegmark talks about different versions of the multiverse. So 1, 2, and 4 were the cosmological multiverse, different patches of space. Now, this third one has to do with quantum mechanics. We're talking about something completely different, right? So again, this is one interpretation. It's due to Hugh Everett, and Sean Carroll is another important proponent of it today. So let's start with the first question. Do you have waves or particles, right? So this is a complicated story. Basically, what happened is that indeed people thought that light was a wave due to Thomas Young's experiment. And then Einstein has shown, this is actually what Einstein won his Nobel Prize for, that photons of light are actually particles. This is the discovery of the photoelectric effect. So Einstein showing that what we thought were waves actually acts as particles. Whole separate discussion as to how exactly he has shown that. Slightly later, but approximately at the same time, Louis de Broglie, so Einstein is one of the founders of quantum mechanics, Louis de Broglie is one of the founders of quantum mechanics. So notice, quantum mechanics is called quantum mainly because certain interesting properties come in discrete chunks, quanta, right? So for example, the energy of a wave of light comes in discrete chunks, individual photons. This is why this is quantum theory, right? So Einstein shows that waves are actually particles. Waves are actually particles. So waves of light are actually made up of individual particles, which are photons. And de Broglie, in his PhD thesis, shows that particles are actually waves. Long story, whatever, right? So, and a double slit experiment is a good way to illustrate that. So double slit experiment, basically, in this, again, you can watch a million videos explaining this better than I will right now, but there are regimes in which the electron or a photon, the biggest thing with which this was done, as far as I know, is a buckyball atom. It's a C60 atom. C60 molecule. So you take 60 atoms of carbon, 60 atoms of carbon in a particular shape. So this is a molecule, C60 molecule. You understand? It's a molecule which is made of 60 individual atoms of carbon. And you can do this double slit experiment even with such a huge, by quantum mechanical level, object. And the idea is that, again, in certain particular circumstances, a photon, an electron, or a C60 molecule behaves like a wave. Now, specifically, when we talk about waves, we're talking about Schrödinger equation. So Schrödinger equation is a wave equation. It's a wonderful story, whole separate video about how Schrödinger actually, came up, basically invented his theory, wave mechanics, out of thin air. And he saw waves, but in reality, we don't see electrons and photons as waves. It's like if you look at an electron in a cloud chamber, it looks like a streak, it looks like a particle. So Schrödinger actually hoped that his wave equation is only going to have like integer solutions which like the equation will evolve towards a stable configuration, and this did not happen. And so Schrödinger was puzzled about that until Max Born came in and said, you know what, Schrödinger, your equation talks about waves, but not waves in space, but we are talking about waves of probability distribution. So it's like an electron is not a wave, but the Schrödinger equation describes the probability wave of an electron. So if you imagine, let's say, a bell curve distribution, at the peak, this is where you're more likely to find an electron, and in the troughs is where you're less likely to find an electron. And again, notice in quantum mechanics, not everything goes. Certain things happen with probability 100% of the time. Some things just never happen. So it's like if you have an electron, let's say you pass a photon through a beam splitter, through a particular silver mirror, it's called halfway mirror, I forget. Anyway, so it's like spontaneous parametric down conversion, I think is the physical term for this, right? So you generate two photons with opposite polarization, or let's say in a Stern-Gerlach experiment, you generate two electrons with opposite spins, right? If one electron is spin up, the other electron is 100% spin down. So quantum mechanics isn't about anything goes, right? Some things always happen with 100% probability. Other things just never happen. Now, but the problem is that quantum mechanics in this sense is either is incomplete or points to a deeper indeterminacy in the fundamental laws of physics. So it's either incomplete or the universe is indeterministic, right? So either the QM is incomplete, specifically the Schrödinger equation is incomplete, or the universe at bottom is indeterministic. So I opt for the second option, for the first option, that quantum mechanics is incomplete and at bottom everything is determined. I'm going to have to do a separate video as to why is that. It's like, but we don't know. It's either or, and the choice is still open, right? In the 21st century, the choice is still open. It's just for methodological, philosophical reasons. I think that determinism is an easier way to wrap your head around, right? But at the end of the day, we don't know. We have different formulations of quantum mechanics, right? And so, so wave function collapse observer, I should point out, right, so Felix was talking about observer effects, right? So when we talk about quantum mechanical observation, this is a physical interaction, right? So in the double slit experiment, you put a detector interacts with an electron in a particular fashion. So maybe to oversimplify, imagine you are bombarding an electron with a photon such that the photon bounces back. So obviously your act of so this isn't about consciousness. So observation is not about consciousness, it's about interaction. And when you interact with these very small, very tiny particles, it is impossible for your interaction not to mess with the particles. So it's like, if you imagine an electron and you bombard it with a photon energetic enough to bounce back and see how it was reflected, how it was scattered, you will impart some energy to the electron, right? So you cannot observe the system without disturbing it. There's more to that. I'm oversimplifying a bit, but this is one level. So ultimately, what we're driving at is that when you look at these experiments, you can have different interpretations. We should do a whole separate video on somebody do your presentation on the Schrödinger cat. We'll talk about that, right? So one standard interpretation is the so-called Copenhagen interpretation, due to people such as Niels Bohr and Werner Heisenberg. And basically, what Bohr and Heisenberg would say is that the universe at bottom is indeterministic. Or in fact, they have this positivist agnostic interpretation. Like, when I am not looking, I have no idea what goes on. This is the Copenhagen interpretation. And many people, me included, Sean Carroll is another one. Einstein was definitely very dissatisfied with this description of quantum mechanics. Another way let's talk about objective collapse models. Objective collapse. So some people are going to say the Schrödinger equation isn't enough. There's actually some mechanism that causes the wave function to collapse. So GRW is one objective collapse model. Another one is Penrose. Roger Penrose has ideas about everything. So he also has ideas about this. So there would be a notion that, again, quantum mechanics, Schrödinger equation is incomplete. Like this equation is incomplete. There's other interactions which cause the wave function to collapse. I could talk about this, or do a presentation about it if you want. Now, for my money, the most, I think, philosophically parsimonious, the easiest to understand interpretation is the de Broglie-Bohm pilot wave theory. De Broglie-Bohm pilot wave theory. Do I have it somewhere? I'm sure I've had it somewhere, because it's going to take me time to type this out. So the Broglie-Bohm pilot wave theory. This is the simplest interpretation. If Felix tried to explain this, he'd be able to explain this no problem. So the idea is that you say sometimes light behaves as a wave, sometimes as a particle. Sometimes electron behaves as a wave, sometimes it behaves as a particle. So the pilot wave theory says it does so because it is both. There is a wave, a pilot wave, and on top of this wave, there's a particle which rides on top of this wave. And so basically, in addition to the Schrödinger equation, you also have the wave, the guiding equation, right? So this is the simplest, most visual way to explain away all the spookiness of quantum mechanics. And the Broglie-Bohm pilot wave theory is completely deterministic. It is a completely deterministic, it's a deterministic and realist interpretation of quantum mechanics. Determinism and realism. But it is non-local, and people don't like non-locality, and also it's not very mathematically elegant. So, but it's non-local, which is probably fine because locality is probably not true, and it's mathematically inelegant. Mathematically inelegant. So, if I had to bet, I would not bet a house on the Broglie-Bohm being true, but I'm not even sure I'd bet a car, but I'd bet a laptop that something like the Broglie-Bohm is true. And the most important objection against the Broglie-Bohm is that, again, it's mathematically inelegant. It doesn't work very well with quantum field theories. So the theory that Felix is going to talk about is Hugh Everett's many worlds interpretation. And Everett is also a deterministic interpretation. Is it local? Well, it's weird. Locality, I don't think locality is defined quite the same way. So, but it is completely deterministic. And the biggest proponent of this is Sean Carroll. Feel free to look at his idea. And basically, what the many worlds interpretation is going to say is that the particle goes through both slits, but when the particle goes in the double slit experiment through both slits, the particle branches, but you branch as well. So if you think of the Schrödinger cat, right? So in one branch of the multiverse, the cat is alive and you saw it alive. And in another branch of the multiverse, the cat is dead and you saw it dead. So it's like the cat branches and you branch at the same time. So Tegmark's cosmological multiverse, they are far away, very far away. The quantum, the parallel universes of quantum mechanics, this many worlds interpretation, they are not far away. They are, in some sense, in exactly the same location in space. They are just like orthogonal in a different dimension. They are in a different dimension in Hilbert space. But they are, so to speak, in the same position in classical space. Something like that. If you didn't understand that, don't worry too much. But again, if you want to do a presentation on this, feel free. And again, the best material to use is Sean Carroll's book, Stanford Encyclopedia of Philosophy also has very nice articles. Sean Carroll's book, Something Deeply Hidden. Anyway, let's go back to Felix.
And one of the ways to explain, and it, as crazy as it sounds, a way to actually explain why the wave function collapses is to look into multiverse. And it says that quantum physics doesn't apply to just one universe, but many multiverses. The electrons is, to describe the wave function, is in all of these spots at the same time. But once we observe it, we know which universe we are in, and that's when the wave function collapses. So you don't...
Yeah, so again, so Schrödinger had this problem, right? So his electron looked like a wave, but we actually observed it as a particle, right? And so what Everett does is he says, no, the electron actually is a wave. So there's a continuum of places in which, electron exists in all of those places. But you observe it only in one particular location in space. So it's like the wave function of the electron branches, but your wave function branches as well. So there's potentially infinite, well, in the double slit experiment, there are 2 slits. Electron goes through both. There are 2 electrons, but there are also 2 of you. And each of you observes the electron only go through one slit, right? So in the similar fashion, when an electron just travels through empty space, you have a continuum, potentially infinite, right? Continuum of possibilities of where the electron is, but there's also a continuum of yous, right? Of you, multiple copies of you, and a continuum, you understand, right? So not a discrete set, but potentially a continuum. And you always observe the electron in a given spot, and that's a way to go from the strict formalism of Schrödinger equation to the observable reality. Now, the reason why physicists love the many worlds interpretation is because it's very parsimonious mathematically speaking. Pilot wave theory is mathematically inelegant. The de Broglie, the many worlds theory is very mathematically elegant. Now, it's very counterintuitive. It's not the world we see. We don't observe real world superpositions, but mathematically it works best. It's this one by far is the simplest formulation of quantum mechanics, in fact. And I'm sure this is not a very clear explanation, but I'm just going to have to promise that we're going to come back to this topic at some point in a future video. But let's finish with Felix right now.
Know which universe you are in until you observe it or make the measurement. So each universe has a copy of each particle. Does that make sense? I think it doesn't make sense. It shouldn't make sense. So you probably heard about the Schrödinger cat experiment where, with the exact same principle, where you have a radioactive material that randomly decays. So by probability of quantum physics, the cat inside a box will die or live, depending on this random chance of probability. But we don't know the outcome until it's being observed in the same form of it's sort of a way to put this collapse of the wave function to our scale, where we don't know. It's 2 things at the same time until we observe it. An electron is a wave and a particle until we observe it. The Schrödinger cat is both alive and dead at the same time, and it's theoretically possible until we observe it. So a way to explain this, and I think it's an easier way to understand multiverse, is that the cat lives in one universe, the cat dies in another universe, and we don't know which universe we are in until we look inside the box. It's the same sort of principle. So this sort of opens up the door that our universe is constantly being split. We're splitting our universes depending on and creating infinite copies of infinite outcomes. And it opens up the idea that anything that is possible within the realms of physics is possible. So there's another universe where I am still the #1 subscribed YouTuber. There's another universe where I'm still making hot dogs like I did how many years ago? There's another universe where I just decided to finish university. I don't know.
Yeah, so I suppose I should mention, so it's very important, it's not that your choices branch the universe, it is the branches of the universe physical branching of the universe, which affects your choices. You cannot split worlds by making decisions, right? No, the universe splits for physical reasons, and then for physical reasons, this is a physicalist model. You make different decisions in different branches. This is one thing I wanted to mention. So, and also, I suppose maybe to comment on what Felix is saying in a different fashion. Again, so the biggest problem of quantum mechanics is that elementary particles, fluctuations in the quantum fields, sometimes behave as waves and sometimes behave as particles. So basically, what de Broglie-Bohm does is it says, yes, you sometimes see particles, sometimes see waves, because actually there are 2 things at the same time. There's a pilot wave, and on top of a wave, there's a particle. There are 2 things, and you observe 2 aspects of this interaction, right? So what the many worlds does is it says that there is a wave, but the wave is spread across the multiverse. But, the physics is set up in such a fashion that even though the Schrödinger equation is a wave on the level of the multiverse, you only find yourself in a particular patch. And so, if you want, like, an aspect of you observes an aspect of an electron. And that's why you are one thing and you observe an electron as one thing. But if you are able somehow to perceive the multiverse in its entirety, you would see that you are actually, the entirety of you is your wave function, which is spread across the many worlds, and the electron is spread across the many worlds. Like one spread, another spread, but they meet only in one point. And that's why a singular you only sees an electron in a singular place. I have no idea if this makes any sense, but that's my best attempt at an explanation.
These other, roadblocks that you can imagine with your own life, that each of these possibilities and each of these universes exist according to the many worlds theory that explains the quantum wave function collapse. 42 minutes. Time will cut it down. I hope I did a good job. I don't think I did, but I tried my best. I find this so fascinating. Dude, why would you want to believe in all this other shit that people make up about, dumb shit, right? There's so much cool stuff that we can theoretically think about our universe. And I think what's fun about this is not just understanding that it's possible, but kind of, at least in some matter. Obviously, we don't know the math, I don't, at least. But in some capacity, understanding how it works. To me, this is fascinating. And I just had a lot of fun collecting all this information for myself. And I just wanted to share it with you guys, basically. So that's what this video is. If you enjoyed it, let me know. Smash like, subscribe. I really appreciate it. And I'll see you in the next one. Purpose.
You thought he was gay, but true.
Yes. Thank you, Felix. Thank you so very much. This was amazing. If this was a presentation in class, this would be a hell of a presentation. Now, a bit too chaotic from both Felix and from me. This is super difficult. I don't expect anybody to have been able to understand this very well unless you're already familiar with this stuff. But again, as Felix said, it's a fascinating topic. And, anybody who learns about this stuff wants to share it. And this is Felix's best attempt to explain this in simple terms. And this is my best attempt to react to Felix and to explain this in simple terms. I'm not sure if this was clear. Probably was not very clear. So I'm going to take this as an invitation to do more videos on this topic in the future. Hopefully to try to explain this better, because this is one of the topics that we talk a lot about in our Philosophy of Science course. In general, Felix, thank you so very much for these videos, if nothing else, because they stimulate interest in these kinds of topics. I'm not sure if this was clear, but I certainly hope it was fun, it was enjoyable, and it piqued your brain at least a little bit. I'm gonna refer back to this in future lectures that hopefully we're gonna have. So, this is materialist worldview in which consciousness and brain is just a product of mechanistic forces, right? So if you want to see ethical and political implications of this worldview, my course on Coursera, Introduction to Political Philosophy, is live today. The link's in description. If you're not interested in that, you're just interested in philosophy of science, the 2021 course, I have many videos on my channel, but the 2021 course, the lectures are every Tuesday. I'm trying to record them ahead of time. We've only had one lecture and one Q&A session so far, but we're going to continue down the line. Colleagues, if you have any questions, comments, anything, feel free to let me know. If anybody wants to take an aspect of this, because probably, again, Tegmark talks about 4 levels, so these are probably 4 individual presentation topics. If you want to take one of these as a presentation topic, feel free. So this has gone for quite a bit of time. Again, this was tremendous fun. I'm not sure if it was clear, but it was fun, a bit too much fun maybe for me. So colleagues, thank you for joining. I deeply appreciate your participation and your comments. Honestly, it means a lot. So until next time, stay safe. Take care, and I will see you around.